Say a lot better. Today we have Ben here. Ben works at Kaggle. How many people know about Kaggle? Okay, so that's awesome. Cool. That's great. So Kaggle, Ben can talk all about it. It's an online, how to describe it? It's basically like arranges a bunch of competitions in machine learning, and has done that for many years and has been very successful doing so. Has, I don't know how many 100,000 machine learning people doing, submitting competition, taking part in these competitions. So he's going to talk about that, so I'm super excited about that. And that's all I'm going to say, so thanks so all for coming.
Am I wired up or no?
You are, but can you stay centered just because it might give feedback?
Awesome. Thanks a lot for the introduction. I'm really excited to be here tonight. And I'm here to speak with you about both Kaggle competitions and the future of reproducible data science. But before I get started with that, I'm curious to learn a bit more about who came here. So raise your hand if you consider yourself a data scientist. Cool. About 20% of the audience, it looks like. Now raise your hand if you consider yourself a software engineer. Looks like, okay, wow. This is going to work well for my recruiting pitch at the very end then. And raise your hand if you are not, consider yourself non-technical. Awesome, that's one person. And then, let's see, it looks like almost everyone's familiar with Kaggle. Keep your hand up or raise your hand now if you have a Kaggle account. Wow, about 80% it looks like. And then keep your hand up if you've made a submission to a competition. About 50%, and keep your hand up if you come in top 10 in the competition before. In that case, I should just let you give this talk because you'll do a better job of it than me. And then finally, keep your hand, or raise your hand if you've rated a Kaggle script or Kaggle kernel before. 0 people. Awesome, okay. With that, let's go ahead and get started. So as almost all of you know, Kaggle started off running machine learning competitions. We've released challenging machine learning problems to our community from all around the world, which is about 680,000 data scientists now. And then we get about 100,000 submissions to these competitions every single month. So they've been a really exciting way to grow our vibrant community, as well as get exposure to a lot of really cool problems in machine learning. And since 2010, we've run over 200 general competitions, as well as offered about over 1,000 competitions for university classrooms as a more exciting way to learn and applied way to learn about machine learning than starting off with a textbook. Then that's put us in a really fortunate position to be able to learn a lot of lessons along the way. By virtue of running all these competitions, we've learned about what techniques work well. We've learned how people go about winning competitions and what qualities that the people who tend to win competitions have. We've learned why our community participates and enjoys competing in competitions. We've also learned a lot more about what major pain points data scientists are hitting, both in their day-to-day jobs, as well as we work with companies that are interested in hosting competitions and data scientists who are competing on our platform. And then finally, how can we help data scientists ameliorate these pain points? So to get started and really ground this talk, first I'm going to look back at two recent competitions that we posted. The first of these competitions was with Santander Bank, and it's on predicting customer happiness, which by itself can be a really complex problem. And in its realization as a machine learning competition on Kaggle, it was a standard but more straightforward form to work with. It was a standard binary feature matrix, or standard feature matrix with several hundred numeric features and about 150,000 sample customers. There wasn't too unbalanced in that there are at least single digits of a percentage point to work with in one of the class examples, and then it was a binary classification problem. And one of the things that we've noticed is simple competitions generated an absolutely incredible amount of participation on Kaggle. Pretty much every time we host a new simple and straightforward to start with competition, it breaks that new participation record. So this has been our most common competition so far, with close to 100,000 submissions and 5,000 teams from around the world competing. And with that context, let's take a bit of a deeper dive in how that competition progressed what the results were. So if we look at the best submission results over time, we started off on day 1 with the baseline solution of the evaluation criteria. In this case is a metric called area under the RC curve, which is 0.5 is random, 1.0 is perfect, and for a lot of problems, 0.8 is either really bad, really good, or somewhere decent. In this case, it's a good result. And then it started off here. Within the first 24 hours of the competition, the performance immediately shot way up on the problem as people applied a lot of state-of-the-art technologies to it, ingested the data, and used their standard processes. And then very quickly, people hit a wall that they could not surpass. However, if I looked at a graph of participation over time, as time progressed, more and more people got involved in the competition, and the bulk of the submissions actually came later on in this. So this wasn't the lack of trying, it wasn't the lack of 5,000 brains tackling the same problem, nor was it a lack of resources. Just to give you a sense for how the public leaderboard and final leaderboard relate to each other in this competition, when we post normal competitions, we have 2 sets. We have a set of data that people get feedback on immediately, and we have a set of data where we withhold the results until the very end of the competition. In some competitions, those results can become disentangled due to something called overfitting. We'll talk about a bit later. In this competition, they were really highly correlated with each other, with only a tiny little bit of overfitting. That was at the very top end of that. And then the top 10 teams in this competition were also all incredibly close together. We're going to go down to many decimal places to figure out who actually won the competition. Just to give you a sense for what this looks like on the scale of the evaluation metric we're using, this is, again, where rating was on this metric. This is perfect way over here. And then the entire 3 months of the competition occurred in this tiny little arrow here between the best submission, and I use a 24-hour participation baseline as my normal baseline measure in a competition, because it represents what you can kind of quickly do on a problem, applying standard techniques, and then the best final result. So just to blow that out, there were over 1,000 teams and 23,000 submissions that occurred within a very narrow window that for most practical purposes wouldn't be significant. And then just to also compare, the best public result was released during the competition with the final results. The best public result, which was right in the middle of that narrow window, used about 10 minutes of compute, used a straightforward pre-processing step, and then used XGBoost, a popular implementation of gradient boosted machines with optimized type of parameters. And then the final result of the competition used days of compute, many complex feature transformations and embeddings, used complex validation and cross-validation strategies, and finally had dozens of clouds that were ensembled and optimized together. So this type of result is a really recent phenomenon that's emerged in some of the simple competitions that we post, and it would not have happened 5 years ago. So what's changed? First, the tools for working in machine learning prompts in a standard form have really matured over the past 5 years, especially those in the open source ecosystem. One thing aside of that, we have a substantial fraction of our community who uses closed source tools like MATLAB and SAS. No one's ever run a competition using any of those. We've had many guys that have emerged, like scikit-learn and Python, that enable consistent and rapid feature exploration and model selection across a wide range of models to make it really easy to plug and play models and figure out what might work best for a given feature set and problem. And then finally, best practices have emerged and through a lot of painstaking trial and error for applying machine learning to these types of problems that we are given in this kind of standard form. And then for machine learning problems like this, the lesson now is that if you're really trying to improve your results in the problem, it's clearly not the case that throwing brains at, or if you're managing a data science team, having a team dedicated on a year, purely on machine learning piece, is going to be a use of time. And instead, that time is best invested in formulating the problem structure, really creatively extracting the relative properties and exploring unstructured data that might have a possible impact, as well as understanding things like distributional changes in the data that could impact its realization and problem over time. And then continuing with the in-depth exploration of that narrowly defined machine learning model space is not a good use of time. And then just to provide a couple more pieces of evidence for this, we can dive deeper into the actual submission results that teams made. So this is looking at the top 2 submissions for the winning team and the second place team. And the winning results were very highly correlated between the two, meaning they were predicting the same customer satisfaction scores for individual customers in the set. And then if we generalize that across the top 10 teams, each of their submissions, that entire set is almost entirely correlated. Just to explain what this graph means, because we're going to see it again in a little while. This number here, this axis means that each submission is actually appropriately correlated with itself. The first place and second place teams, because they're bright red, are correlation close to 1, they're highly correlated, and so on for the first place team against the fourth place team, etc. And then a final check that I use in many competitions is trying to ensemble winning teams and top place teams to see if it meaningfully improves results. And in this case, as expected, it did not result in any meaningful improvements because I'm ensembling a bunch of things that were very highly correlated and almost exactly the same. Then I started off with that competition to provide a point of contrast with one of the other competitions that we posted recently, which is one of our most complex competitions today. And this was focused on automatically answering 8th grade science questions. And then complex competitions, some of the most interesting competitions we posted actually have some of the lowest participation rates too, because the problems themselves can be fundamentally hard to get started with and hard to make improvements on. So this one had 300 participants and 170 teams that were really active in the competition. And just to give you an example of the types of questions that these are working on, all these are 8th grade multiple choice questions, so it's things like which of these is going to control in an attempt to reduce the depletion of ozone and the Earth's atmosphere? Actually, raise your hand if you think it's A, methods of filtering gasoline. B, use of core CFCs. Okay. I'm not going to bother going down with the rest of the results. Congratulations, you passed the first 8th grade science question, but don't feel too confident because the computer did as well. However, that one was one where all the top 20 models did well. All the top 20 models didn't do well on all the questions. To give an example of a question that they did poorly on, the single most basic unit of all things, living and non-living, is a molecule, a cell, an atom, or DNA. Of course, we all know that atom is the basic unit of all things living and non-living, because non-living is in there. However, the cell is described more commonly in source data texts that these arguments may be using, like Wikipedia or other structured things, since biology is talked about a lot as a most basic unit of life. And then the algorithms look at it and say, okay, most basic unit, see that, see living, life, okay. That of course grid for I'll try to hire for probably like this cell and we'll atom, and then that's where it goes wrong. It falls over like this here and button. So to compare this with the other competition I showed, where all the competition, outside the first 24 hours, operated within the tiny window that was barely visible on the projector, this competition actually had a really dramatic improvement relative to the baseline, and this also was a problem that had a meaningful baseline on it. So even though this competition had a small participants, a small number of really talented participants, and generated a really meaningful improvement of the results. However, a human result of this problem would probably be something on the order of 96 to 100%. Some of the questions there was wanted to debate with what the actual result answer was, but somewhere close to 100% anyways would be your exploitation. And then the top computer model was only at 59.3%. So the current state of the art in a problem like this is a computer scale and a trade science test. Now I'm going to do that same type of analysis to compare the top submissions against each other from the previous problem. This problem, it turns out that the top submissions each will only agree with each other a small fraction of the time, about 50 to 60% of the time here. So this points to the top submissions approach the problem in different ways. solve the problem in different ways, or potentially could leverage insights from each other to get better results. Another way to visualize this is looking at the test set questions here at this axis. There are about 2,000 questions in the test set, and then the team's correct answers and whether or not they were correct or incorrect. So this is ordered by the questions that the computers all got right to the questions that the computers all got wrong. You can see here that there's a class of questions that they all got right, like the one that I showed you to begin with. There's a class of questions over here that they all got wrong, like the cell and most basic unit question, which would have been Adam, and points to like a lack of maybe understanding of the underlying text. And there's a lot of insight that can be gotten out how to go and try and predict models based on the types of questions that all of these are missing. As well as in here, there's potentially insight from sets of questions that some types of models get right and some types of models get wrong. And for an example of one of those questions that half the models got right and half got wrong, you see is here it's a physics question, and two of the answers actually have the exact same words in them: changes in velocity over time, and time over changes in velocity. But a lot of the methods that actually did well in this competition and were used effectively did not depend on the order. So you see very clearly why it would get a question where the only thing that matters is order, half right and half wrong. Then again, unlike the previous competition, looking at the results of this competition, on some point our results improves the overall performance of the system, so you can generate very meaningful improvement simply by applying the results of many of the top teams. So this really illustrates both that there's a long ways to go on this problem. The expectation of us when we posted this was that many of the winning results would come from the more state-of-the-art techniques like recurrent neural networks that include things like order, and then a lot of teams tried to use those, and then actually we're less effective right now, given the status quo, than information retrieval style techniques, all of which characterize the top 5 to 10 solutions. And then we know that information retrieval techniques are inherently limited and have clear failure modes on this problem, and it really points to there's a lot more work to do on it. And then finally, one of this clever trick I wanted to highlight that one team used for training that worked very effectively and helped essentially improve their results was, instead of having it as a 2-class classification problem within each of the answer choices, is the same sort of correct or incorrect, and then go with one that maximizes the probability, had the max probability of being correct. Actually treat it as a 3-class classification, is it first answer, second answer, or another answer, and then that training trick led to a much more stable model that specifically improved the results. So there's a lot of little tricks that you can use along the way in the framing of a problem and how you approach a problem that's independent of both the feature selection aspects as well as the machine learning selection aspects. It was one of the top 3, and I do not remember which one. And the other parallel or contrast I wanted to draw here is how you can look at results like this versus how results are currently presented in academia. If you pick up a natural language processing paper that runs an applied model, you simply see a table like this where you have a list of data sets, a list of problems, a list of models and techniques, some of which are supposed to be listed as state-of-the-art, and then you're showing that your model did better on some combination of data sets than every other model that was there. However, this is a really limited form to share results in because you can't actually dig into some of the richer insights that you get if you have the individual predictions submitted by the models and then can compare, is this model effectively highly correlated with this model, or is there some interesting set of cases where this model is getting right, whereas the current state of the art is getting wrong? So one of the things that we've started doing in a small number of competitions, and we hope to extend beyond that to help address this, is not only show the winning score, but where it's possible, actually release what the winning submission files look like. And then, as well as a solution file for the competition, which can enable some more interesting analyses and insights to be generated from that. Just one early example of this is we run a just for fun March Madness competition every year for a computer March Madness bracket tournament, and then for the one of the visualizations we create from that is the probability each team has of winning games based on here's a distribution of all the different machine learning model predictions. Okay, so with that as a grounding point, I want to take a step back and draw some of the lessons and themes that we've learned across competitions. First, I was working on an axis from simple to complex when I characterized the two competitions earlier. We can look at that more generally, where simple competitions or simpler competitions are more straightforward to approach and are characterized by things like being a standard binary classification or regression problem, having a relatively small sample size, but not so small that you can no longer apply machine learning effectively to it, having a single feature matrix that's either numeric or categorical data, things like that. Whereas more complex problems might add on temporal or spatial structure that really confound a lot of results with highly correlated features and outputs, as well as more complicated prediction structures like multitask learning, where you have a partially shared set of inputs and many different outputs that you're trying to predict instead of a singular output you're trying to predict, or real-time standard evaluation metrics, as well as complex input data like audio, video, images, neural patterns. Then how this is materialized is if we categorize competitions as from simple to complex and that, you see that roughly similarly when we look at the evolution of model performance over time. Here, we're looking at generalization of the graph I showed earlier, with the start date of the competition here, the end of the competition way over here, and then model performance where 0 is the baseline, in the first 24 hours of the competition, and 1.0 is the best result at the end of it. The most simple competitions that we've had in straightforward ones to address look like this, which are characterized by really dramatic performance improvements over time, followed by a quick tapering off and a wall that you can't surpass, no matter how many more computers or people that you throw out the problem. That if you're running a research team, the lesson that you learned, or what you really want to know is, are you at the wall for that problem? Or is a breakthrough likely to emerge? Or as problems become increasingly complex, then you can be seeing more and more performance improvements over time, but still characterized by more dramatic ones at the beginning as the quick wins are made, and then slowly accumulating additional more incremental wins later on. And then the most complex problems, which show little performance improvements at the beginning, and then over time there's arbitrary jumps in performance as people find discoveries or investigate different nuances of the data. Actually, by the way, if you have any questions as I'm going along, raise your hand or stand up, and I'm happy to take those along the way too. So another pattern that we've seen across competitions is that there's, over the past year or two, there's two techniques that really dominated almost all the competitions that we've run. Either gradient boosted machines or deep neural networks. Gradient boosted machines have tended to work well in the simpler problem types, the ones that aren't necessarily enriched hierarchical data, but reduced to feature matrices that are straightforward to work with. And neural networks have tended to work on the ones that have a rich compartmental hierarchical structure like images or speech or audio data or videos. And just to give some examples of these, convolutional neural networks were key input to all the winning models for the retinopathy prediction competition, where the stream data was all images of the eyes, and the prediction was whether or not the participant or the patient had disease called diabetic retinopathy, and a numeric score for how bad it was. Another one where convolutional neural networks were key for was automatically estimating heart volume. Ejection fractions, which has been calculated in heart volume based on images they were used in feeding the heart. And by the way, both of these first two examples, the argument performance was effectively the same level as human performance on the problem. Third one, where recurrent neural networks have been powerful, is in EEG signal processing, so things like seizure prediction. And one surprising number of deep neural networks were actually effective was an early competition that we hosted with it involved a multitask problem. We're actually predicting 15 different targets. It had a lot of molecular features about the molecules to predict in different ways how they would impact body. And then neural networks are able to take advantage of that more complicated structure to the problem and actually do better than other methods. Then pretty much for everything else, outside of some of the types of problems I mentioned here, XGBoost has been a key part of the winning solution. Second is really key theme that's emerged is for almost every competition that we posted, model on sampling has been a key part of the winners. It has almost never actually resulted in like a revolutionary performance gain. However, it's almost always resulting in a slightly more stable and slightly more robust model, with an order of 1% to a 5% performance gain. That brings us to some things that competitions aren't currently very effective at. So we're really focusing on optimizing a single evaluation metric right now. And by virtue of that, we're not optimizing things like model complexity, so we get many really complex solutions as ensembles of ensembles. The advantage of this is it is straightforward from an engineering perspective to figure out which one's performing the best in the simple version that's performing the best, and then take that out of the ensemble. We also get many teams codes that look something like this. That's a complex mess of spaghetti code. So it doesn't really yield production. It isn't helpful in yielding production code that can fall straight into production, even though a lot of you say that you're software engineers. I've seen many software engineering teams that also write code like this. We also don't currently limit computational resources, so we reward machine learning model performance without computational complexity, and encourage people to burn a lot of CPU resources that way, which again doesn't help out with model productionalization. On the flip side of that, they are very highly effective at some things. The first is I see competitions like a powerful laser. If you have a single evaluation metric they're trying to optimize, then it shoots right at that single evaluation metric and encourages a really massive exploration of what's the possibility space to do that. So one way to look at that is like with a competition that had 5,000 people, hyperparameter optimization, model selection by over 5,000 people, each individually going through explorations. Another thing that it's really good at is fairly consistently evaluating a variety of approaches on the same problems. One of the real challenges in research is implementation details really matter. So in situations where you don't have the raw data or raw code, it is really hard to have to compare your model with someone else's model or someone else's approach. And that also leads to one of the jokes that we use, which is if you want a quick, simple way to apply machine learning in your domain successfully, look at the recent research papers published in it, then pick part of the student baseline that every research paper is claiming to be, and implement the student baseline, because that will almost inevitably work really well. They're also really effective at exposing a niche problem domain, like a subproblem in particle physics or a specific medically EG problem, to a really broad community from around the world and diverse community around the world, and getting that community excited and passionate about the problem. And that brings us more to the human side of competitions. So as I mentioned earlier, we have about a community now of 700,000 data scientists from around the world who participate in competitions. And who are these people? About a large fraction of them work for small and medium businesses. A large fraction of them are students that are coming to learn more about machine learning, or learn computer science, or are interested and curious about machine learning and AI. Smaller number are either postdocs or professors or other researchers, and a decent fraction also work for Fortune 1000 companies. And then why do some of these users come to Kaggle? People coming to learn is the single most common theme from our user base, and a very applied way and an effective way of learning our problem. Because it's one thing to read about something in a textbook, it's another to learn about it by banging your head against trying to get something to work in practice. Many others come to demonstrate their abilities in data science and machine learning and use that as an entry point for changing their careers. Smaller fraction would also come to evaluate a machine learning technique that they think would work well, and then see how it actually works in real world problems and to access real data, since a decade ago it was really tough to access real applied data, and a lot of times you're stuck working with factual and theoretical problems. Many of us come for a fun community. One of my favorite reasons I've heard is because on a Saturday morning it's more stimulating than Sudoku. To give a couple of examples of how users have successfully used Kaggle before, Francois Cholet is author of deep learning package Keras, which is a very effective package to apply deep learning in a simple API instead of majority API to a problem, and also rapidly iterate over deep learning model architectures. So he first shared a lot of code on that on Kaggle, and then saw that since it was effective, very quickly get adoption with our community, to the point where 6 months later, almost every prompt that was farmed with deep learning was also using Keras as a way to approach it. In a similar vein, Chen used Kaggle to help generate the control voucher for XGBoost, which is the common gradient boosted machine implementation I mentioned earlier, which has the advantage that it's really fast and efficient to work with, as well as sort of nicely that it can be designed from an API perspective. Another user got a job at Facebook after doing really well in their second recruiting competition. Would like to come back. He was actually the one that designed and set up their most recent recruiting competition that they ran with us. And then finally, Google DeepMind's had the habit of approaching many of the people who went computer vision competitions in our community and then when conquering them. So here's one example of that. And so how do many of these people win competitions? It's clearly not just applying Keras or applying XGBoost, but that's common knowledge and everyone does it. One of the really common themes that when participants have is they think about their approach deeply and set up their workflows to optimize the speed at which they can iterate on a problem, and don't kind of go off on month-long tangents investigating one approach. So they build their execution speed and iteration speed and really explore many possible approaches to figure out what will work. So that gets through this loop of identifying handling dependencies that are processing, extracting and selecting features, training models, and visualizing results. So that's a good pipeline for that. It gets through that as many times as possible. And tools like Git, it's like GitLab and ggplot2, all help make that more efficient. Also, the successful competitors tend to be creative in all aspects of the data science process that they can approach with competitions. So everything from going to which source assets that they can use in some competitions where they can bring their own data to how they split the data sets and train their models and do the feature extraction. It's not just for the machine learning piece, it's also applying creativity, like I mentioned, the Allen Institute challenge to, instead of training on what the correct answer is or the probability of this answer being correct, train on 3 classes, the probability of the first one or the second one being correct, or saying no, it's not any of these choices. And then almost all winning solutions have some aspect of creativity in one or many of these elements. Just another example of this is a visualization from one of the winners of the Brad-Mounthy challenge that he used to evaluate his models. So at a glance, you can very quickly see everything that you need to know about how his model training was progressing and whether or not you need to tweak something and to compare with the previous result. Most of the successful participants tend to be really dedicated and tenacious as well. It's really rare that someone wins a competition after making 5 submissions or 10 submissions, instead of constantly approaching the problem over a 2 to 3 month period and making hundreds and hundreds of submissions on that problem. They also like overfitting. This is one competition where a small group of teams overfit the leaderboard, where you see for most of the range of the leaderboards, public and private scores were heavily correlated. And then at the very top of the leaderboard, people actually had showed improvements in the public leaderboard, whereas their scores actually went down in the holdout set. And one participant, Gregory, had a funny story about this. He was swimming in second in one of the competitions he was participating in. It was his first competition. He was constantly refreshing the leaderboard at 5 p.m. Pacific time, which is when the deadline kicks over, and now you can see, thinking, yeah, how did I do? How did I do? And when he refreshes it and shows up the final result, he was in the first place. Nope. He was hoping he would have moved from second to first, didn't make there. Didn't make second place. Then has to start scrolling down the page until he figures out he landed in 50th place because he overfit the problem. That is the single most effective way to teach overfitting. Again, I think probably he's not overfitted competition since. So, ready? these competitions also means that we've seen many thousands of pain points in that science. Actually, for those of you, or anyone who's experienced these pain points before in your own work professionally or side projects, I'd be curious if you're easier. And so one of them is trying to get access to that data. It's really tough, even sometimes if you work at the organization, to get access to the data means it lists in separate business units or silos that you don't have your credentials for, or you have some bureaucratic red tape to get through. If you're at another organization or outside of it, then it adds yet another piece of red tape, and it makes it that much harder to get access. The second piece is getting access to high quality data is even tougher. Many of the interesting data in the world and valuable data in the world is still either in PDF documents or in printouts that haven't been digitized. That where in Excel spreadsheets or other forms are tough to work with programmatically and automatically. This leads us to the third pain point that's been an incredibly common theme, which cleaning data can be incredibly painful. Just some examples of that from competitions that we posted. This is a tough thing to see, but this is a list of columns in one data set that we looked at when we're exploring hosting prostate surgery competition. Hundreds and hundreds of features. There's this one feature in there that when we ran a baseline model, and it turned out to be almost entirely determined of the target was a obscurely named feature called prostate. Turns out that feature represented the patient had prostate cancer surgery, which is actually incredibly predictive of whether or not they had prostate cancer, and is entirely useless in any practical scenario. We've also had like thousands of other examples, like plane cleaning before they take off in one data set. Bulldozers manufactured in the year 1000. We had hundreds of thousands of bulldozers manufactured in the year 1000 because someone thought 1000 was a great number to use as a missing value. Web essays and essay scoring competition that we hosted, that was supposedly not a really good score. Just that this essay got good marks, but as far as I can tell, it's Studerbridge. Turns out that one of our transcribers didn't follow the instructions that they should discard any essay that they couldn't read and not put it into our system. That's just a small number of many pain points that we've seen with big data. And yet another one is going from research to production can be really difficult for many systems. So if you look at how research teams operate or data science teams operated, companies, they'll start off with offline analyses, figure out something that they face an improvement, then they'll go to implement it online. In many cases, there's pain points in shifting languages from languages and research or systems and research to optimize for exploration and iteration to production systems which are optimized for low latency and robustness and reliability, so it takes longer to get it implemented in production than they expected, whereas they thought they would be sitting here on a happy trajectory, good results. And when they actually go live, they find out that there was an assumption that was missed or something was different than they expected, and it actually hurts the performance. The biggest pain point of all that we've seen and experienced can just be summed up with in one word: reproducibility. So before we talk about that, let's look at this panda. This panda had seen web is just go down the slide. It works well for him. He thought, okay, that was fun. He goes down the slide, lands like this. The other panda looks at him and was like, well, work on my machine. And then first slide worked for me. Then the first panda goes back up, goes back down, flat, lands like that. Didn't work for him the second time. Then looking at this in a more practical sense, I'm sure many of you are familiar with the SAPs, and it's like the introduction to machine learning SAPs that's commonly used for integrated visual recognition. I was given a quick demo of using a demo script a while ago. They wanted to rerun, went back to that, and it just didn't work. They think, how many Python users do we have here? We have well, okay, 80% or so, 85%. I'm sure anyone how many Python 3 users do we have here? There's not enough hands raised now. I'm sorry for the other half of you that didn't raise your hands. So for the ones that raise your hands, I'm sure all of you hit this very frustrating error when you try running Python 2 code in Python 3. So that was the first one that I did anyway, to try going back to using that code. I was like, okay, fine, I'll go through and convert this to Python, create a modern syntax, updated that, rewrite it, did the second error. Well, I uploaded the file, whoops, forgot to put the data file that depended on where I needed to go. Okay, so did that, rewrite it, the third error. Turns out that since the script was created and I was trying to run it again, the API for Keras changed. So Edward Einstein has this great quote, and Xavier is doing the same thing, but we're going to break in and expecting different results. To modify it for the state of data science right now, or status quo data science. So data science is sort of the same thing over and over again and getting the different results. And for a more helpful example, I could bring Anthony to create the first version of the graph that I showed earlier for one competition, and I was curious how it would apply to another competition and some of the other competitions that we posted recently, because I thought it was a really interesting way to frame the analysis. So in principle, I need to change two things. I need to say, run this in a different competition, and I need to say, here's a function to calculate the submission similarity, because we can take a lot of different types of submissions for competitions. They have different forms, and there's different similarity metrics that can be used based on the competition. So in principle, it should be a 5-minute change. In practice, to actually do this, once I got it implemented, this is a case where I could actually get the code. I had to downgrade my Python version. I had to install array of new libraries. I had to manually download the top submissions for each competition from the way we had that set up. I had to start Jupyter notebooks and load the notebook file to use. I had to write all the cells corresponding to the Jupyter notebook, then debug the really frustrating set of error messages, and then finally, after all of that, to actually get to the point where I could change the parameters I needed to change. That I should have just been a 1- and 2-step process to begin with. So the status quo for a lot of data science teams right now is it's really tough to build on top of that and others' work, even if you sit right beside them. And then even expanding outside of that distance, one of the coolest papers I've seen recently from machine learning research was a question and answering system that's looking at an image, then using that image as an input to a text role within a system. So I thought this was a really cool paper. I wanted to experiment with the results, to get a better understanding of how it worked. Then, as I go through, I see there's no code or there's no computational environment that's released that would help me do this. So if I had several months of time, maybe I could go to reproduce the results. But in practice, I didn't, for something that was a valid Keras, they didn't have several weeks of time or months of time to go through and to try to reproduce those results, which meant that I didn't take the next step by virtue of the barriers that were in place to simply reproduce work that someone else had already done. So I see, like, a lot of the best software engineers that work with are incredibly lazy. They hate going through front work and repeating groundwork. So if they do the same thing twice or 3 times, they'll automate it and figure out a way not to have to do it a 4th time. On the other hand, compared to that to data science, a lot of data sciences looks like we're doing the same groundwork over and over again. And that's because the tools that we have to work with in the current state of the ecosystem is decades beyond the development ecosystems in software engineering. Let's kind of keep an eye on. So that brings us to what Kaggle's been going out and what we're rolling out to try addressing and supporting this pain point. Over the past 14 months, we've been developing a new product called Kaggle Kernels, which if you go to the site right now, you'll see about 20,000 reproducible code examples that people have shared on Kaggle from within the community. And then we see a kernel as a single additive of reproducible data science. So it combines the 3 fundamental building blocks: version code, version data, and a version computational environment through Docker containers. We see that all the core inputs to that are currently there. We do not think that there's anyone's created like the glue layer that connects them together in a delightful user experience yet, or the cultural change to mean that actually gets used. And we combine this together and we get a single piece of reproducible data science work. So the first step that we took for this is we released it mid last year on our competitions platform as a review script or where you can drop in any competition you're running now, things like that. And what that does is that immediately drops in our Python or Julia environment that has a data preloaded into that environment. So you can run and explore the data set there. And these environments are backed by Docker containers. So we maintain like Kaggle/R or Kaggle/Python Docker container you can go and pull and work with locally as well. Where we try keeping all of the commonly used R libraries and stuff like that. So things like create, most of biostats, most of the common packages in R, fit similarly in Python. For all the Python users out there, how many have had trouble installing Python libraries before? They're very frustrating building errors. So we've been trying to work around, provide a serial image that works well across those pain points. And the other unique thing about this environment is that right now, every time someone runs something or published in this environment, it's published as soon as it's run. So that means that we're building up a really rich code library for any competition or that we posted. Whereas before, we went to do one of the competitions that's over a year old. In a given competition, I might see 3 or 4 different kind of getting started examples that someone uploaded a Python file or linked to a project in GitHub for. Then, by virtue of making this easier, now this collaboration piece or public collaboration piece of competitions has exploded, where I see over 100 times more shared collaboration now in competitions than I did a year ago. And this spans the gamut from here's a machine learning model to help me start in a competition to here's an exploratory insight with a single feature in the competition to here's something that's interesting about the data that's completely irrelevant to the competition. The other really helpful thing about this is it makes reproducing and building a topic about another's work simply a click away because it drops you back into the same environment they used to create the virtual result and lets you interact with it and explore it there and then go and build on top of it. And we have Jupyter Notebooks now enabled for a custom user interface in this setup as well. We're big fans of Jupyter and IPython notebook set, Kaggle, and many of our communities. That's a great question. Yes. But not quite yet. There we go. So the first step that we took is enabling this on the Kaggle competitions that was a good fit for. The second step that we've now taken is enabling this on non-competition data sets, where you can go and do about a little over 100 data sets we featured that have been published through Kaggle now that range from information about the 2016 election to a database of European soccer teams. And then when you're looking at getting the data set of Kaggle, unlike if you go to data.gov or if you go to many other sites, and I think the Visual Researcher site, you have a little link to a CSV file, and that's about all the helpful explanation that you have on the data. If you're really lucky, they may have decided to put a header on the CSV file so you actually know what the columns are. Many times you're not that lucky. But if you publish a group Kaggle, you get all the value that other people are adding by working with the data set, and then you can click through and see the code examples that they create on that, which could serve as starting off point for you understanding the data set. It could help you loading the data, which means you don't have to rewrite the Python code or PR code that goes from a file on disk to a file in memory that you can work with to inspiring more of your work. So the goal here again is not having to reproduce or work or recreate work that people have already done, and instead enabling you to start from the current state of the art and current understanding and build on top of that. And the future one of the types of things that will enable on this as well is the concept of a crowdsourced data dictionary, where you get all the metadata that from if someone sees such as 1,000 represents a missing value in this column, they can add a comment that you see when you load into that column that be aware there's a bunch of confusing values in here, here's how to do them. Maybe better down the road in a pipeline sense, they create a pipeline step that reprocesses that to perfectly represented as a missing value, and then everyone else works from the clean version of the data, where they can still go back to the starting version if they needed to, if there's something going incorrectly with the data set, for example. And now, about a month ago, we launched the ability for any user or organization to publish data sets in our platform for other users to create and build reproducible analytics on. So we see this as a endeavor that we're just getting started on. Our longer-term mission is to help the world learn from data. We see that we can have the most value there by working at the intersection of people, of data, and code, providing the global layer that really works effectively at that intersection. And means down the road, they will be able to access any public data set in the world through Kaggle in a standardized way. Look at all the code that's been created on top of that when you're trying to deploy the public data set in your work, and then eventually be able to use the platform for your own work more directly. And before I open it back up to questions, I'm a shameless plug. If any of you happen to work with C# in the audience, I'd love to talk. I'm currently hiring C# software engineers. So thanks a lot for taking the time to listen to me. Private data sets? And the answer is not yet. I'd be very interested in more and more about your use case.
You get a problem as an experiment, and then you say, okay, now I'll put the data in, but private data can't show it. So the user can say, well, you decide to process the user, and then you can do that.
That point.
So I noticed in some of the more recent competitions that the data sets are getting bigger and bigger. And I wonder if you guys have any plans to make computing power more accessible. Some of the data sets are so large that you have to have a baseline access to some sort of cluster or even GPU instances to do anything meaningful. And so kind of creates an uneven playing field. I was just wondering what you guys think about that going forward.
One of the operating principles that we use is we try to work with all the different types of interesting machine learning problems that we can. So one outcome of that is that we don't turn down problems because they have larger data sets or because they're data sets that might require a large amount of compute to solve them. One of the actual interesting things that we've seen is many of the high compute or assets that you think would require a lot of compute, in some cases, one of the top, say, 5 or 6 teams actually approach the problem with a small desktop computer or a relatively small amount of compute, and through down sampling or through a creative means, found out a way to do well on that without spending a lot of money on compute resources or being as part of our organization that to enable access to a lot of compute resources. We absolutely want to make it easier to access larger amounts of compute through the cloud. We've heard and experienced a lot gain from using the current set of cloud services to access our large amounts of compute. So we don't think there's a good user experience around that right now, especially from a data scientist standpoint. But at least near term, there's a financial constraint that we can directly subsidize.
Regulars for the competition. Tonight, top with like 230 submissions. Some of the people below that is hard killer. And if you look at, is there any merit to any of the top 10 result of 5 submissions stuff like that?
Let's see, I think the question is there any merit to submitting 5 times versus 200 times in a competition? And the observation is that many teams win with 200 submissions or after having submitted many times, and some other teams win after only making a small number of submissions. I think in most competitions, there's no merit in having more submissions within the submission cap for the competition. And what that is more of a byproduct of the teams being really active in the competition and using it as a sanity check throughout the process of their activity. So I think that they would have been effective had they made 5 submissions. But given that it's an option to make submissions and score yourself against the public leaderboard and compare that to other scores that were merged, it's an option that may be mistake.
I guess I don't understand the public-private leaderboard concept. Is there some ways in there to
That's a good question. So to clarify that, every competition has 3 sets of data. Starts off as two, a training set and a test set. We give the training set to every participant with the answers on it. We give the test set to all participants without the answers on it. That test set is then subdivided into two sets, a publicly awarded and a privately awarded set. That is a completely distinct subdivision. In most cases, participants don't know which individual network of data fell into the publicly awarded or fell into the privately awarded. And then the public leaderboard set is only used for the real-time leaderboard during a competition, which is a really powerful motivator because if someone beats you on the leaderboard, you want to do your best to beat them and so on. And then the final evaluation leaderboard set is only used and only shared at the very end of the competition for awarding final and rank prizes and placement. And then there's no additional noise or any overlap between those.
So I had a question about how the competitions are done. So it seems to me like the simple, we kind of divide it into two categories. One fairly simple problems where at this point most people kind of know the answer is fairly straightforward problem solved. Others are much more open-ended and much more unknown. And the ones that are, even the ones that are simple submitted from the mission, the difference between 82.6% and 18.9% sort of who's the winner. So based on the sampling of data, that's within random noise maybe. And so, between us, we're kind of a meaningless result, actually, that's a small difference. And so I'm just wondering, is there some better way to help us learn as a community to show, that this is sort of the right answer for those sorts of problems? Maybe to judge some more advanced problems differently, because maybe, rather than having a single metric we're judging on, and the creativity to apply all these problems, there's been very different approaches and Republicans have learned from each one. Maybe it's comparing after the Florida, you can't really compare correctly.
So there's a lot to that. I'm not going to go through the effort of our question because it was I think a little bit hear it. So every single competition title has a single evaluation metric for data and score against.
Use mic.
Let's see. Let's see. Okay, it's working. Okay, we'll give this a try. It's working now. So every single competition on Kaggle's had a single evaluation metric that it's scored against. And in some cases, it's not always the case that the top two teams are within us, are statistically are different enough from each other for that difference to be statistically significant. That can be a frustrating experience for participants, but it's not a problem that we're really in a position to address directly, because from a competition prize standpoint, if those equating to other prizes explicitly defined up front, in terms of including how many get awarded and what the amounts are, and you can't change the distribution very easily based on things after the fact, as well as from a host perspective, that means that each of the models would, in theory, work very effectively for the competition. So the ones that do have in that case, it says, from if you're interested in moving farther, it's not the most interesting problem to work on, or it's like you need to do something beyond how the problem is currently framed. If you have a lot of solutions that aren't statistically significant from each other, especially if they all land in the same part of the solution space.
So a lot of the problems you talk about being reproducibility related, but not things that are totally different from what you experience with any software from one computer to another, versus packages, whatever. But another major problem that we talked about briefly was this annotation in code. And I think that happens a lot more in data science than many other fields of software. Do you have any plans to address that?
Yeah, so if I go into a working directory of a lot of data scientists, and I'll see that the version control is something along the lines of model 1, model 2, model 3, model 4, model 5, model 5, final, model 5, I swear this time. then I think there's kind of two aspects of that. One aspect is that a lot of data scientists do not come from software engineering background and haven't learned to follow what good software engineering practices. And then the second aspect is that a lot of what data science work is, unlike having to go look into a production software system, it's fundamentally very iterative. You're not trying to refactor it to be the best flow. Instead, you're trying to write a lot of experience quickly to figure out how to narrow down the results that you have. So the approach that we're trying to take in that case is the reason that they're labeling it that way right now is it can be hard to go back, or if they don't know how to use Git, it can be hard to do that with a version control system, and instead your file system is a version control system. So to swap the mindset of you keep the same file, then every single thing that you're doing is tracked by another system, and then you can go back at any point in time within that system to see what the previous version and the output of the previous version was. So you don't have to invert your own your own version of data control, version control just for that system project. So if you look at how that's materialized right now in kernels, we've not integrated with Git for conversioning yet. We only work with SQL driven output files or SQL Python or script files. So we're going to send simple linear version history through that. Down the road, we're going to be providing a nice UI on top of that. We can start off with a single version history for how many data scientists currently operate, and then for those that are familiar with Git, they can take advantage of the full power of Git and GitHub. Say that there are more hands up. Cool. We'll save those hands disappear. Thanks a lot for having me. It's great being here.